Welcome to the second presentation in Unit 6 entitled The Wave Equation. It says quantum mechanics brought an unexpected fuzziness into physics because of a quantum uncertainty, the Heisenberg uncertainty principle. So you generate this, and that is actually called the wave equation. Now, this is what happens when you apply the wave equation to the atom, and we're not talking about that at this particular point. So instead, we're going to keep it a whole lot more simple, and we're going to refer to this as our version of the wave equation. Okay, what we wanted to know is that there is an inverse relationship between period and frequency. We want to identify the factors that affect the velocity of a wave, and we want to use that particular equation. So here's what we already know. We already know that there are two major classifications of waves. There's transverse and longitudinal. We've talked about mechanical and electromagnetic waves, and we've also talked about the key vocabulary terms related to waves. Now, here's what we learned in the lab. The speed of the wave depends on the media at which it travels. If you were to increase the tension of the wave, in other words, you were to pull the spring tighter, the speed of the wave changes as well. So we already know a little bit about waves in the sense that we can apply what we know, what we learned earlier this year. We know that waves travel through space, and since they travel through space, that means they have some sort of displacement. So they travel a certain displacement, and they do so in a certain amount of time, so we say that they have speed or velocity. Since they have speed or velocity, we can apply our velocity equals distance over time formula. The wave speed actually varies depending on the medium in which it travels. For example, the speed of sound in air is 343 meters per second, whereas if you move to water, it's 1500. And if you move to steel, it's like 4500. So the speed can vary depending on what it's traveling in. Likewise, you have light, and light actually travels at 3 times 10 to the 8th, or 300 million meters per second, which is much, much faster than anything that sound can do. Now, rank the waves from fastest to slowest. Okay, so the fastest one is most definitely going to be light. Light is number one because it travels faster than anything else in the universe. Number two is generally going to be sound. Okay, it is going to be sound. And number three is going to be an ocean wave because ocean waves are going to be the slowest. It says, what can you do to increase the velocity of a wave on a string? Well, we've already decided that the speed of a wave is related to what it's traveling in. Now, once I've established that I'm going to use a particular string, that string right there has a certain velocity. The only way that I can change the velocity of the wave on the string is I can increase the tension or how much I pull that particular string. And that's what the knobs at the top of a guitar do. Whenever you twist that knob, you're actually pulling that string tighter and you're actually allowing the wave to travel at a different speed. When you allow the wave to travel at a different speed, it ends up sounding different as a result. Okay, it says, what is the velocity of an ocean wave that travels 100 meters in 12.5 seconds? So I'm looking for the velocity, which is the same thing as speed in this particular case. Say distance, time, and I would say 100 meters in 12.5 seconds. As a result of that, I would say V equals D over T, or 100 divided by 12.5. At that point, you would get your calculator out. You would say 100 divided by 12.5, and you would end up getting a value of 8 meters per second. Okay, next, this is a student looks into the night sky at a star that is 1.5 times 10 to the 19th meters away. How long does it take that light to travel from the star to reach your eye? So I'm looking for the time that it takes in this case, and I know that the velocity of light is 3 times 10 to the 8th meters per second. That is a constant for light. I also know that the distance that it has to travel is 1.5 times 10 to the 19th, and at this point I can say velocity equals distance over time. The velocity that I have is 3 times 10 to the 8th. The distance that it travels is 1.5 times 10 to the 19th, and I can solve for the time. Now, when you do this, a lot of people have a tendency to divide by 1.5 times 10 to the 19th. You can't do that because the time variable would still be on the bottom. Instead, what you want to do is you want to switch these two places, and so you would get time is equal to 1.5 times 10 to the 19th divided by 3 times 10 to the 8th, Whenever you do that, you would put it in your calculator at this point, and you would get a value of 5 times 10 to the 10th, and that would be in seconds. Now what that means, whenever you get that answer, is that it takes about about 15,800 years for the light to travel that distance. As a result of that, when you look at that star, you're actually not looking at that star, but you're looking at how that star looked 15,800 years ago. So a lot of times people refer to astronomy as looking into the past. The second part of this particular presentation is that you have velocity equals lambda f, and we're going to call this the wave equation or the velocity equation. What it refers to is it relates the velocity, which we've already established what velocity is, to the terms for wavelength, which we defined in the previous presentation, and frequency, which we defined in the previous presentation. So we're relating velocity directly to the distance between peaks, and frequency, which is the number of cycles per second. So match the variables with a unit. The frequency is defined as the number of cycles per second. Velocity is defined as the rate of displacement, and wavelength is defined as the distance from crest to crest. Now, a lot of people will take a look at this formula and say, how does this actually work in terms of, I thought velocity was distance over time. Well, remember, wavelength is a distance. It's the distance between peaks. So when we say wavelength, that really is like a distance. And then a lot of people say, well, frequency is not time. How can distance times frequency give us anything? Well, frequency is the number of cycles per second. When we're talking about time, time is the number of seconds per cycle. So they're inverses of one another. So when you say frequency, what you're really saying is 1 over the time. Well, if you, instead of frequency, if you put 1 over time, well, you have a distance term, you have a time term, and you have distance over time. Now that's just kind of showing you where it comes from. We're still going to use the formula V equals lambda f. That's what we use. So we move to the next one. It says the speed of light is constant. As the frequency of light increases, the wavelength does what? And so if you look at this, velocity equals lambda f. If this term is a constant, in other words, it cannot change, if I were to change this value, if I were to increase the frequency, if this goes up, in order for this to remain the same, it's because this must go down. So if you were to double the frequency, the wavelength would half, because it's got to be the original constant value. Next, it says determine the velocity of an ocean wave if it has a frequency of 3 hertz and a wavelength of 5 meters. So you would say velocity equals lambda f, or 3 hertz times 5 meters would give you a velocity of the ocean wave of about 15 meters per second. Okay, and finally it says if this wave has a frequency of 200 FM, where FM is 1 megahertz, then what is the velocity of the wave? Well, a megahertz means times 10 to the 6th. So when I were to say frequency, frequency would be 200 times 10 to the 6th, or if you're putting it in the right scientific notation, it'd be 2 times 10 to the 8th. It says this particular wave. Now this is a tricky question because remember, the distance between identical points is what we call the wavelength. What they show you here is not the length of one wave, but it's the length of 2 waves. As a result of that, you would have to say that the wavelength is not 3 meters, but instead it's 1.5. And then you can solve for the velocity. Velocity equals lambda f, or 1.5 times 2 times 10 to the 8th, which gives you 3 times 10 to the 8th meters per second.